Hello, I am Dimitris, and this is my colleague Alex, and we're really happy to be here. We are from GRNET, which is the Greek National Infrastructures for Research and Technology. And together we will discuss about AppStack, which is an open source cloud native platform for running digital public services. And we will also discuss about the story behind its development. Here is our presentation roadmap. We will provide some information on GRNET, what it is, what it does, and what is responsible for. And right after that, we will provide a number of challenges regarding the operation of digital public services. Then we will describe our platform, which we call AppStack, and how its different open source components are able to tackle different problems. Finally, we will list some key experiences we obtained while operating the platform in production. GRNET started as, and still is, the Greek National Research and Education Network in Greece. Just for the record, each country has an NREN, as we call it, which is a specialized internet service provider dedicated to support the needs of the research and education communities within a country. Specifically, GRNET provides internet connectivity, infrastructures, including cloud computing, high-performance computing, and various advanced services to the Greek academic and research community, and also to agencies of the public sector. Here are some numbers regarding our infrastructure. Our network consists of 10,000 kilometers of optical fiber, includes 340 points of presence in 50 cities, and it connects more than 150 entities, including, as I said before, universities, research centers, also hospitals, and other public entities. In addition, we operate 6 data centers placed at 3 different geographic locations throughout the country, where more than 120 racks exist and include more than 2,000 servers. Overall, and up until 2019, we have been operating various infrastructures and services, including different cloud offerings, e-voting service, monitoring services, and others. And all that up until the summer of 2019, where we learned that we will maintain our NREN role and keep operating the aforementioned services, but also we are going to be highly involved with the digital transformation of the Greek public sector, which was not an easy task given the bureaucracy that existed in Greece at the time. Specifically, the organization became responsible for the development, operation, and maintenance of the gov.gr portal, which is Greece's public sector information website, and several governmental services, including the electronic issuance of documents signed by the Greek state, and the digital wallet that Greek citizens can use to control how they share identification data, among others. The advent of the COVID pandemic made the implementation and the maintenance of these services more urgent and critical. The electronic issuance of documents signed by the Greek state is of particular importance because there are hundreds of different document types included. Such documents involve formal declarations, private agreements, certificates, and of course, the COVID certificate. Offering services for the general public introduces a set of challenges and considerations that differ from those associated with services targeted at the academic community. Some key issues involve: 1, faster development and deployment cycles. The initial goal was to launch some services in a very short period of time. And also we expected continuous feedback, for instance, based on new legislative amendments that should be immediately reflected in the services that were already up and running. 2, scalability and resiliency. Such services need to handle a large number of concurrent users and scale to accommodate potential growth. 3, security. Services for the general public require robust security mechanisms that can protect against, of course, DDoS attacks and other application layer attacks. Finally, public perception and reputation. The success of such services is often tied to public perception and trust. If you think about it, citizens trust that their interactions with such services are reliable and efficient, they are more likely to use them. To cope with our new duties and demands, our teams, including first and foremost our SRE team, together with developers and our security team, developed AppStack, a cloud-native platform with an enabling environment for integrating open source software components. Currently, AppStack is maintained by GRNET's SRE team and hosts hundreds of user flows for governmental services. Now, Alex will provide you some technical details about the platform.
Hi. So, we had a vast legacy infrastructure that we maintained as an SRE team. We knew that the coming changes need a paradigm shift to modernize the way we were running services. So, we set up some goals for what we wanted to achieve. We decided to embrace new to us technologies, mainly containers and CI/CD. Containers as a robust way to define any software running in our infrastructure, and CI/CD as a way to automate any testing and deployment processes. We also wanted to make all tools and procedures self-service so they can be used by whoever needs to. What we hoped to gain was faster hands-free deployments, hands-free meaning we are not required to run the deployment process ourselves, proper service overview, meaning we had concrete points where service-related technical information was defined, and faster scaling of resources. To achieve those goals, we made a few decisions. COVID-19 made us speed up the timeline of this change, so we wanted to minimize risk by focusing on the new features the platform would give us. So the decisions were: define an internal platform that the SRE team runs and developers and service operators can use to efficiently run their services. Invest in self-hosted Kubernetes setup as the basis for all service workloads. We evaluated other solutions, but 2020 was about the time where it was clear that all other options for container orchestration were becoming relevant. We also decided to trust open source tools and our own experience to compose an agile and configurable solution for our needs. GRNET is an academic organization, and we prefer open source solutions. There were vendor solutions that promised all-in-one products, but we felt that we were better off to avoid any lock-in. And because we're already invested in running our infrastructure, we decided to keep using what worked already. We had a working VM infrastructure based on our cloud offering. We had a working Puppet ecosystem that manages all our VMs, and we have backup and monitoring solutions ready to use. Next, we decided to keep databases and all other stateful components outside of Kubernetes. This doesn't really need an explanation. We knew that database resiliency would be important, so we opted out of cloud-native solutions. And lastly, utilize our existing hardware infrastructure to provide the base for the platform. We had more than enough server resources and the required know-how to deploy them to production already. This is a service-level overview of what we envisioned. We decided early on to use Helm as a package manager and deployment tool for each service. We deployed Harbor as a plug-and-play Docker registry for those artifacts. So we had a software repository where each commit is built as a Docker image and pushed to the registry. Then we had the respective deployment repository where a job is triggered to deploy any changes to the cluster. All services run on Kubernetes clusters. And we have a monitoring stack that gives an overall view of the events happening on each service. Both teams, SRE and developers, can access all components for debugging monitoring purposes and for operations. This is the infrastructure level view of the platform. Internet traffic, either from the rest of Greece or global from our upstream, is routed through GRNET network to our own DCs. The platform has 3 layers. We have a network layer, a load balancer layer, where all requests are routed to the clusters. we have the Kubernetes workload layer where all service workloads run, and the storage layer that contains the database and other storage backends. All layers run either on physical machines or on VMs on RDCs. All components here that are on Kubernetes were reused from previous setups. We already had a storage appliance that was used as a persistent storage volume backend for all clusters. We also deployed an internal object storage service based on Chef for the services that needed it. The first part of the architecture are the load balancers. This is how we bring HTTP traffic to clusters for all services. We use BGP between RDC routers and the load balancers. We have dedicated IP prefixes to assign dedicated IPs for each service. We then run HA proxy in TCP mode on all load balancers to route all requests to the Kubernetes clusters. And then we run ingress and NGINX in node port mode inside the clusters, which in turn routes all traffic to the relevant backends. Next up are the Kubernetes clusters. We deploy all clusters with KubeSpray. KubeSpray is a project that uses Ansible playbooks to manage a kube-button cluster. That was, at the time, the most maintained project we found for running self-hosted clusters. We decided early on to have multiple clusters for different grouping of services and have different clusters for separate environments of those services. Each cluster has a series of infrastructure components that support the services running the cluster. Services like ingress and NGINX, flags for GitOps, bit for log shipping, Prometheus node exporter for metrics, etc. We have a database cluster outside of Kubernetes. We chose Postgres as the main database solution due to our familiarity with it and its widespread usage in the Python ecosystem. We have a highly available cluster with one leader and multiple replicas. We use repmgr as a cluster management tool for failover and replication control, and PG Bouncer as a connection pool for our bigger services. We have a monitoring stack that covers infrastructure and service metrics. We deploy those tools on Kubernetes and follow the same principles as the rest of the platform. We use Sentry for error reporting, Elasticsearch and Kibana for log aggregation, and Prometheus Grafana for graphing and metrics. Our infrastructure components are evolving over time as we want to offer more advanced features to all services. We expanded ingress and NGINX, which already included mod security, to handle application firewall duties. The feature was developed with our security team, who also handled creating custom rules tailored for each service. We send all logs to Elasticsearch and present them to the relevant service dashboards. This covers the infrastructure part of the platform. Now Dimitris is going to speak about our experience running gov.gr on production.
Okay, thank you, Alex. As you recall, hosted services include the electronic issuance of PDF documents signed by the Greek state. Now, such documents involve affirmations, authorizations, and EU certificates related to COVID, for instance, vaccination. Now, these user flows, as we call them, are currently over 320. This particular service is a Django application developed by GRNET's developer team. Note that to generate such documents, the service employs different templates and interoperates with other third-party services hosted on other infrastructures. Up until now, 8.5 million distinct citizens have used this service, and around 300 million of transactions have been performed. And when I say transaction, I mean that it's an entity that usually, it's something that usually takes 2 to 4 minutes, where a user interacts with the service to issue a document signed by the state. And as I said before, such transactions include authorizations, but also user input provisions, preview and consent actions, and PDF downloads. During peak hours, our infrastructure is able to deal with 20,000 requests per second and yield up to 6,500 documents per minute, which mean around 100 documents per second, something that you can see clearer in this figure after I describe it. This figure presents the 10 most busy days that AppStack has ever encountered. Time is on the horizontal axis, and generated documents are on the vertical. During this period, which is January 2022, Greece was under lockdown, and every 2 days, Greek students had to generate COVID-related documents and report them back to their corresponding schools. Usually this took place during the afternoon, as seen in the sudden increases, where a significant influx of visitors appeared in a short period of time, meaning 3 to 4 hours. During these days, AppStack was supporting the generation of more than 1.7 million documents per day. This figure presents the aggregate number of the different transaction types that have taken place throughout the years using our platform. On the horizontal axis, we have time again, starting from 2020 to today, and the vertical axis corresponds to millions. Note that the sharp increases in the number of transactions usually coincide with the launch of a new user flow. Through our monitoring services, one can also observe trends such as this one, where we see that on a Sunday evening, transactions where Greek citizens are generating different documents drop abruptly when the European Basketball EuroLeague final starts. Now, let me enumerate some experiences that we have obtained while operating AppStack. Our architecture allows for multiple deployments per day, even with thousands of users connected. We can respond to changing conditions and feedback quickly and minimize the impact of an issue by promptly implementing and deploying a solution. Notably, during the pandemic, the policies that were related to the various services running on AppStack were decided in a national operations room and communicated by phone to the technical teams. This doesn't sound too nice, of course. But the teams, in turn, implemented corresponding changes and deployed the updated services within minutes. By carefully monitoring different metrics, such as request and response times, success rates, connection pool usages, and others, we are able to tune parameters, including the number of application workers, pods, and other elements, in order to keep the system from reaching several bottlenecks, e.g. database I/O limits. At some point, during a substantial increase in the number of users, our monitoring system could not process corresponding metrics and collapsed. However, the services continued to run successfully because they were decoupled by design and run isolated from each other. As I mentioned earlier, there are actually third-party government services that run on other infrastructures and interoperate with the services hosted on AppStack. On numerous occasions, managers responsible for these third-party services notified us that their services could not handle the increase in traffic. To manage such situations, we regulated traffic through our platform, absorbing and delaying incoming user requests to keep the third-party services functional. The platform setup also enabled us to keep all services up and running during a 48-hour data center shutdown that occurred due to extensive electrical work. To do so, we provided power only to the infrastructure, meaning network, computing, and storage, that is utilized to host our platform. All services are constantly under attack, according to our web application firewall reports. For instance, last September, our WAF identified various attacks. We're talking about 25,000 requests. And included different cross-site scripting attack types, SQL injection, and others, coming from different countries, in this case, 10 different countries. Now, our experience from running AppStack indicates that it has potential and it can be of benefit to other governmental agencies, such as cities and provinces, who want to manage their own local cloud rather than relying on the commercial ones. Moving forward, we plan to expand the platform as more services are scheduled. Specifically, now we're working on disaster recovery solutions, and in particular, replicate data and applications across multiple cloud offerings and on-premises environments. We are also working on a method to manage container image vulnerabilities in a more effective way. As you've seen, the platform already enables the periodic scanning of container images via open source scanners, for instance, Trivi, to identify and address vulnerabilities in images early in the development cycle. We also want to dive deeper into monitoring and to elements such as SLOs and observability. We have also written an article where we describe the story of AppStack. The article was published at USENIX Login magazine last sprint, and you can access it online. Thank you very much for letting us share the story of AppStack, and it was an honor talking to you guys. Thank you very much.